Hey there, my name's Gary Sims and this is Gary Explains. Now I really hope you've been following my series of videos about how CPUs work. We've looked at assembly language and machine code. We've even designed our own instruction set for a virtual CPU that we're designing. We've written the assembler for that. We've even written an emulator for that. So really I've been diving into the different aspects of how CPUs work by building it ourselves. After that, I built a clock module inspired by the clock module that Ben Eater created for his 6502 series of videos. If you want to watch his videos, and I highly recommend them, I'll leave a link in the description below. Now I've taken that clock module and I'm using it with an 8-bit 6502 processor to build the foundations of a simple computer with a standard almost, because 6502 was such an amazing processor. It was used in the Commodore 64, the BBC Micro, the Atari 2600 and so many others, Apple II I think, so many other different systems. So we're using the 8-bit 6502 and we want to build our own circuit. Now after you've got the processor and you've got a clock to it, you need some RAM and some ROM. And really these videos came about because I was thinking, oh, I need to get an EEPROM, I need to get an EEPROM programmer, and I need to get some RAM. And I was looking up how much they cost, and some of them are like $60, $70 for a good EEPROM program. I thought to myself, hold on a second, I've got a $4 Raspberry Pi Pico here that can emulate RAM and it can emulate ROM. So that's what I've done. I built a circuit with a 6502, got my clock module on it, and rather than using an EEPROM programmer, I've actually got a Raspberry Pi Pico which emulates RAM and ROM. We can load our program, our 6502 program, onto it and it can start serving it to the 6502. And in the meantime, we get to understand how the 6502 works, how the buses work, the address bus, the data bus, and all that kind of stuff. So if you want to find out more, please, let me explain. Okay, so let's talk wiring. Here is a picture of what we're going to build. Up here in the right hand corner is our 6502 processor. Down here in the bottom left hand corner is our Raspberry Pi Pico, which is acting as RAM and as ROM. Now as you can see, lots of wiring going on here between the two because they obviously have to talk to each other. So let's break it down and see exactly what it is that I have built here. So we'll start by looking at a picture of the Raspberry Pi Pico. Couple of things to notice. First of all, is these GP pins here in green are pins that we can read and write to digitally as we like. And the really convenient thing is down here on the left hand side there are 16 of them. There's also these ground pins, which means you've got 20 pins in total, and 16 which are GPO pins. That's great for the address bus because that's 16-bit wide. And if you look here on the right hand side, we've got 9 of them, which is just enough for the data bus and the read-write pin. In fact, there's 10, sorry, and the clock pin. So what we're going to do is we're going to use this side for the address bus, this side for the data bus. And let's have a look here at the 6502 processor. So, a few things to note. First of all, here is the D0 to D7. It's the data bus, 8 pins that it uses, 8-bit processor. That's what those pins are here. And here we have the address pins. Now they're split up over the two. You've got 0 through to 11, so 12 pins there down the left hand side. Then you've got a few more here, 4 extra ones here on the right hand side to make it 16 pins in total. And this is a diagram of exactly what you'd see here on the actual chip. This is the actual chip. So this pin here is this one over here, this pin here, this one over here, this one 21 down here is this pin over here, and so on. Now, how you know what all those pins are, because if you look at it, that's just a bunch of pins, and even here it's just a bunch of labels. What does RWB mean? So what you do is you look at the data sheet, and this is just one page of the data sheet. But for example, RWB is the read-write signal used to control data transfer. So because this is an address bus and a data bus, are you writing something to memory or are you reading something from memory? And this pin here tells you whether it's a read or a write operation. We've also got here, for example, an instruction of the ready pin. A low logic input on the ready will halt the processor in its current state. Returning ready to a high state will allow the processor to continue. So if this ready pin here is low, the processor stops. So for what we're going to do, we need to tie that just to high, to 3.3 volts, and I'll show you that in a minute. And again, the reset button. The reset button is used to initialize the processor, and this will become important later on because there are 7 clock cycles. And there's a reset vector, which we'll talk about when we talk about how you program the 6502. Here is the reset pin, is this one up here. So that's what we're going to try and build here. And we now need to break this down as a diagram. So there is the full diagram, and it's a bit of a mess. It's, you know, that is basically that in a diagram form. Let's take away some different layers and take it one step at a time. So let's start with the very simple. I talked about that reset button, so look, there it is. What you do is you tie the pin to 3.3 volts through a resistor, and you also tie it to ground through a button. So when you press the button, it will actually go to ground, which will do a reset. And when you haven't pressed the button, it will go to 3.3 volts through this resistor. And if you go back to the diagram, there you can see that pin there. It goes round into the button, which when you press the button takes it to ground. If not, it goes through to 3.3 volts. So that's basically what we're doing. We're building exactly what's showing here on this diagram. Also, other pins we tie directly. So that ready pin we talked about, you always want it to be ready. It is a bidirectional pin, but we don't need to worry about that for what we're doing. And these other pins, which you can find out all about here in the data sheet, but basically these are the ones you need to tie to 3.3 volts. This of course is the 3.3 volts input VDD, and down here we have VSS, which is the ground input. And then the rest of the pins can just stay as they are. For example, this is a clock output pin, so we don't need to worry about doing anything for that. And then obviously the address pins, my data pins, are ones we're going to be using with our Raspberry Pi Pico. Now you also need a clock. FHI2 is the clock signal, and I've got my clock module, which of course I've talked about in another video, which I hope you've watched. And so the clock module is connected to pin 37, and then we also take pin 37 and we connect it down to GPIO 16. Let's just go back to our actual thing here. You can see the yellow one the same. There's GPIO 16, and that goes up to that pin there. Now the address bus, we wire up these ones, A0 through to A11, go round to the first set of pins here, and then these bottom 4 pins here go round the bottom to these 4 here. So again, if we go back to our actual diagram, you can see there you go, those top ones go round, connect up to all these pins here, and then these 4 bottom ones here go round and connect them there, but they're hidden under the blue pins there, which are the blue cables, which are the data bus. So that's the address bus, how we wire it up, and here's the data bus. And so we've got D0 through to D7 all the way mapped over to here to these GPIO pins, and then GP28 is that read-write pin, so it knows whether we're reading to the memory or writing to the memory, reading from the memory or writing to the memory. And so here it is side by side, what we've done, and you can basically see, for example, when I said here that this pin here, the 4th one down, 1, 2, 3, 4, needs to be tied to 3.3 volts. 1, 2, 3, 4, there it is. It needs to be tied to 3.3 volts. Then all the address bus stuff, all the data bus stuff, that's that clock pin goes around there. Here's the reset button. Basically everything as I show here in the diagram I've built here. Obviously down here I've got a reset button for the Pico, and then these little connector linking things you see here, I'm just making sure that all these rails, this is the positive rail here on this breadboard, negative rail here, negative rail here, the positive rail here, the positive on this side, they're all connected together, just to make sure, there you go, that one there takes the 2, just that you've got power and ground on all those rails. And that's basically it. This also shows here the power coming out of the Raspberry Pi. So when you power this up here with a USB port, you actually power up the chip as well. And so if you do all of that, you will actually have a chip, the 6502, up and running, and it can access the Pico as if it was memory or an EEPROM. Okay, so now we've done the wiring, we need to understand a bit about the 6502 so that we understand how it works and how it's going to use the Pico to access RAM or ROM. Okay, so let's talk a bit about programming the 6502. This really is going to be a crash course, not an in-depth course in any way whatsoever. Now, if you remember from my other videos, CPUs actually use machine code, which is basically they read a number and then they know what that number means and they do the instruction associated with that number, then go on and read the next number and so on. And we as humans, we could write the programs directly in machine code. It's not impossible for small programs, very, very hard for much larger programs. So we would either use an assembler, which kind of takes a simple, more human readable way of doing things and turns it into machine code, or even a compiler and use a language like C and then turn that into machine code. Now here are the instructions for the 6502. There are 70, including the new instructions that have been added with this kind of latest iteration of the processor. And really the important thing to understand is that there are three registers: A, the accumulator, X, and Y, and you basically need to do things with those three registers to write your program, putting things in the registers, writing the register content out to memory, comparing those registers, then jumping accordingly, and so on. Now here is a matrix of all of the opcodes. So this is how it defines what does what, and see there are some gaps, for example. So not everything is used. We get some gaps in here. But for example, if we wanted to load the X register, that's this instruction here. Let's say we wanted to load it with a number, and we can see that's A2. So whenever we write load X as a machine in an assembly program, the assembler will convert that into A2, and that's what we're going to look at in a minute. So this is the opcode matrix, and these are all the instructions you can do, and this is a quick explanation of what they do. So now let's go over to actually look at a very, very simple 6502 assembly program. Okay, so here we are with our very, very simple program. We'll ignore all this stuff at the beginning here. Let's just go with this load X with 08. Now, a couple of things to notice is that if it has a hash sign in front of it, that means you actually want to use the number 8 and not some kind of address. And the other thing to notice is the dollar here means that it is in hexadecimal, not just a decimal number. So what we're doing, but of course in hexadecimal 8 is also the same as decimal 8. So we're loading X with the number 8. Then what we're going to do is we're going to decrement X. That's what the dex instruction does. Then we want to store X in the memory address 200 in hexadecimal. We then want to compare X with 3, and notice it's got that hash sign in front of it again, so it's the actual number 3. And then branch not equal to decrement. So basically this will go from 8, it will decrement it to 7, it will compare it to 3. If it's not, it will jump back up here to this label decrement, and the assembler will work out where that is in memory. And we can look at that in a minute when we look at how the assembler converts this. And it will keep going around, and at one point it will compare it with 3, and it will be 3 because it's kept taking 1 off it. And then we just say, okay, let's store the result of X in address 201 in hex, and then jump to start, which brings us back up here again, and it repeats the program. So it's not doing very much other than manipulating the X register and storing things in 200 and 201 hexadecimal. And that's useful because when we start to look at this, we can see whether the program is running. It won't do very much, it will just keep looping around doing these counting, but when we're looking at how our memory is being accessed, we can actually look at that. A couple of other things to note: this .org instruction here tells it, it's a directive, tells it that we want to start the memory at 0. And then right here at the end, we're saying that at the address FFFC, we want to put the label for start in. And then also we've put in this extra word here because we want this ultimately to be 64K exactly. FFFC and FFFD will be the 16-bit address for start, and then FFFE and FFFF will be 0 because we don't need it, but it will give us a full 64K. So why FFFC and FFFD? Well, if you look here at the data sheet, it says when we press that reset button, there will be a reset sequence lasting 7 clock cycles. Then the program counter is loaded with the reset vector from locations FFFC and FFFD. This is the start location of the program. And of course, we've put in there the address 0. So when you reset the processor, it will take 7 cycles to reset. And then it will read FFFC and FFFD 1 byte each. And then it will jump to the address that's in there, which of course in our case is the address 0. So to convert this from assembly into machine code, we're going to use a program called Vasm. It supports lots of different types of processors. Now you can get Vasm from here. I'll leave a link in the description below. Look, it supports all these different processors, including the 6502 family. And here you can find the different downloads, including for Mac, Windows, and for Linux here, specifically for the 6502. You want to download that, and then of course make sure that you can run it. It's somewhere on your path on your Windows machine or your Linux machine, whatever it is that you're using. And then you compile it with this. FBin means it literally produces a binary output, just whatever these instructions are, it produces it. The .dir directive means it understands these .org, things like that, and loop.s is the name of this program. Now when you compile that, you'll basically get some hex. So if you remember, we said that A2 is actually load X. So look at that, it says A2 and then 08. So it's loading X with 08. Next it says CA. Well, let's go and see what CA is in that matrix. So here we are on the matrix. So there is C. Let's go all the way to column A. There you go. Decrement X, which of course was the next thing that we did in our program, decrement X. And then we've got 8E. And then we can go on. Now what I've got here is a disassembly of the program. So actually it shows us that A208 means load X with 8. CA means decrement X. So what did the 8E mean? Well, 8E is actually store X, and then you have the address here, 0002. So it's stored the least significant byte first, and then the most significant byte. And then we've got E0. Well, what's E0? Well, that's compare X. Compare X with what? 3, and so on. So you can see what's actually happened is that that's all the numbers that are stored here, and that is what the assembler does. It converts our program here that we've got this side into these numbers, which is something that the 6502 processor understands. Okay, so just let me show you the assembler in action. I'm using the Windows subsystem for Linux here. I've downloaded that Vasm program. It's on my path, and I have that program loop.s here that we just showed you there in the editor. And we use the command exactly as I showed you, and that will then run, and it will produce a file called a.out. And if we do a hex dump of a.out, we can see it's exactly those things. A2, as we showed, 08 load X with A2 CA decrement X, and so on. So that's basically now our program. Now the final step is that we need to have a program running on our Raspberry Pi Pico that can load in a.out, and then it can present it as the memory, as ROM or RAM, to the 6502 processor. So when it starts running and it says, well, okay, give me the first instruction at address 0, it goes, well, it's A2, and then you need 08, and it starts to run and actually run the program. Okay, so here is the MicroPython program we're going to be running on the Raspberry Pi Pico. Now I'm assuming you're familiar with the Raspberry Pi Pico. If you're not, I've got several videos here on this channel, including an introduction to how you get yourself up and running with the Raspberry Pi Pico. And if you remember, I've got my clock module, and again I show the clock module, the Python code that's running on that. So basically what we do here is we open first of all a.out. Okay, and we basically load it into an array which we're going to call main memory. It's 64K, so the Raspberry Pi Pico can handle that very simply, and we load it as binary because we're not trying to interpret any kind of characters here. This is machine code. We want A2. We actually want the number A2 in hex in that memory slot. Now what we then do here is we define the pins that we used for the address pins and the data pins. And if you remember, there you go, the address pins were 0 through to 15, all the way down that left-hand side of the Raspberry Pi Pico. And you can go back and have a look. These are the pin numbers that were for that data bus. We then have two arrays because we actually need to define those pins as objects inside of inside of Python, which we'll show you in a minute. And then we've got pin 16. If you remember, down in the bottom left right hand corner was the clock signal, and we've got this read write pin which tells whether we're reading to the memory or writing to the memory. Now here is a little function that allows to set some pins to 1 or 0, and it will go through every single one of the pins provided and then set the 1 and 0 accordingly to the parameter that has been set. Basically it says if it's 1 it calls on, and if it's 0 it calls off, and then it shifts the bit over 1 and then sees what it does for the next one. Now we could do lots of printing out while we're running this program. This of course is optional, but for debugging this is absolutely brilliant. So basically I've got a printing out function here, and what does it do? Basically it goes through the address pins and works out what value is on those different pins by using a.value. So that's reading from the address pins. We work out whether we are reading or writing by looking at the value of the read write pin. And we say if the read-write pin is 1, that means we are reading when in the high state the microprocessor is reading. So therefore we go through the data pins, and it basically we need to give it a particular number. So first of all, we set it to be an output because it's reading, and then we set the data pins to what? Well, whatever is in the main memory. What's main memory? That's the program we loaded. Look, main memory is the a.out that we loaded. Whatever is in the main memory at that address. It's just an array. So address 0 is at index 0, address 1 is at 1, and so on. And then we basically are able to read that and set the pins, because that's what that set pin function does, according to the bits that are in that address. So when the microprocessor then reads those numbers, it's reading what number we've put there, and then we set this variable data for our little output that we're going to do down here. If it's the other way around, what we do is we set all the pins to be an input because we want to read those pins and then write them to the memory, and that's exactly what we do here. We say, well, what's the data going to be, and we chunk in these datas by reading in the value for each one. What is it telling us, right? And then finally, once we've got together the word, shifting it left, read the next bit, shift it left, read the next bit, finally what do is we set the memory address to whatever data is, so it gets written to the memory. And then finally we just do some debug printout. We print out the address in hex. We print out whether it's reading or writing, and this is a character that gets set here to R if it's in read mode. The default here is W for write mode. And then we print out the data. Again, there's the data which we've set from here, if you remember, and here, so it's always the correct, whether it's read or write. And then that means on the screen we will see it scrolling past. As the 6502 accesses different types of memory, it will actually display that in our little program here. Couple of other things down at the bottom. When it first starts up, it goes through the address pins and the data pins, sets them all to input. Remember, they do get changed here depending on whether it's read or write. And then finally what we do is we say the clock monitor. What's a clock monitor? Clock monitor is this pin here, pin 16, which is the one with the clock on it. Okay, we basically set an IRQ, which basically means there'll be an interrupt called whenever that signal changes. The IRQ is the signal is going up, so from low to high, it will call our print address read write data function, which is this function here. So basically, every clock signal, it will just print out what's happening on the address bus, and it will also actually do the address bus, so the 6502 can read or write the memory. Very, very simple. In fact, the main part is this big function here, which could be reduced a little bit if we weren't interested so much in what was going on for debugging, but basically that's it. So this is basically acting as the memory controller, or as an EEPROM or an EEPROM, depending on what you want to call it, just allowing the memory to be stored on our Raspberry Pi Pico and allow the 6502 to read and write to it as it wants. Okay, so here is a demo of it running. As we can see, different addresses are being accessed. It's either reading from that address or writing to that address, and this is the data that it's reading and writing from. Notice it's a 16-bit address bus, 8-bit data bus. So what I'm going to do is I'm going to reset the 6502, turn my clock module into single step mode, and then we can go through it one instruction at a time and see exactly what's happening. So I'm pressing the reset button now, turning it into single step mode. Now we know there's going to be 7 instructions, 7 cycles while it resets itself. So that's going to happen here. And ultimately, it will read FFFFC. There we go, FFFC. And what's it reading from there? 0, because that's what we told it in our program to read from there. FFFD, it will also read 0, which means it will now jump to address 0, which it does here. You can see it's jumped to address 0, and it reads from there. And what's it read from there? A2. Well, look here. We know that A2 is the first byte of our program, and it means load X. So we're expecting 08 to be the next byte. So that's what's going to happen now. There we go. 08 has been read in. And then the next one is CA. What does CA stand for? Decrement X. So X will now go down 1 to 7. Then we're into this set of instructions here. 8E0002. Store the value of X in the address 200 hex, 200 hex. So let's see there where we got that comes up 02. Now notice here this one went twice, and that's because in the 6502 the store X instruction actually takes 2 clock cycles. So that's exactly what it is, and you can see that in the data sheet. So now what happens next is we're going to see that it's writing to 200. I've put it into constantly running mode there. Let's go back to stepping mode. What do we see there? It wrote to 200 the value 7, because that is now the value of X. Next we have an E0, that's here. So E0, 0, 3 is compare X with 3. So as we can see here now, it has now branched back round to address number 2, giving us the looking again for CA. There we go at address number 2. And so we're back into 80, and this will keep on going around. Let's just let this run for a second until we'll see that it gets down to 3. Now we have to watch out for the rights. There we go, right there 6, it's written there. Okay, so that's still happening. Right there 6, we're going to see a write to 5 in a moment in that address. There we go. There it is writing 5. Okay, so I can catch it. It's scrolling along. It's quite difficult. There you go, 5. Then we're going to see it writing 4. And there we go. There it's written 4. Now we'll pause it again now, because in a moment we'll come round. Here we go, 80. And then it's now going to write 3 into the address 200. And now actually the branch here is actually not going to loop around, so we're going to end up in this instruction here. So let's see what happens. So we are now into the compare. We're at address 8 here. We are now in the D0, F8, 8E01, here we go, 02, there we go, and now it will do a write, to address 201, and it's writing 3 in there, of course, which is the value of X at this point. And now we're expecting an absolute jump back round to 0. So we see 4C, 0, 0, 0, 0, and now the address goes back to 0, which means we've jumped right back up to the beginning. And of course, what we're expecting to see there, A2 again. So there you go. It's looping round in our little program and running. Of course, you can just set that running and it will just keep doing that. Now, next time we need to maybe connect some LEDs or some other kind of peripheral to this, so we can actually start programming something that can actually interact with the outside world rather than just reading it here on the data stream. Okay, that's it. Now, the one thing I haven't mentioned is timing. At the moment, the clock speed of the 6502 is just 1 Hertz. So it's really not stressing out the RAM on the Pico at all. And also the program in the Pico is written in Python. Now, at some point, if you start to lift up that clock speed, there's going to be some issues that we need to look at. I haven't looked into them yet. Maybe the program needs to be written in C to get the best performance. It will be interesting to see. So in future videos, I'm going to crank up those clock speeds and see how well the 6502 and the Pico can do with each other. But if you are building this circuit, just be aware, keep the clock speeds low for the moment. If you do actually build it and actually get some results, do tell me in the comments below what kind of clock speeds you got out of the Pico and whether the Python program is able to keep up with it. Okay, that's it. My name's Gary Sims and this is Gary Explains. I really hope you enjoyed this video. If you did, please consider giving it a thumbs up. If you like these kind of videos, why not stick around by subscribing to the channel? Don't forget you can follow me on Twitter at Gary Explains, and I also have a monthly newsletter. Go over to garyexplains.com, type in your email address, no spam, but you will get the newsletter. Okay, that's it. I'll see you in the next one.